We take a look here at securing data with IPsec VPN for the protection of IP communications. Early TCP/IP protocol development did very little for ensuring the security of communications between peering devices. As networks evolved, so did the need for greater protection of the data transmitted. Solutions for data protection were developed, from which IPsec emerged as a security architecture for the implementation of confidentiality, integrity, and data authentication, primarily through the support of underlying protocols. IPsec remains a key framework in the protection of data, which has seen an integration of IPsec components adopted into the next generation of TCP/IP standards. So upon completion of this section, it is generally expected that trainees will be able to explain the basic principles of the IPsec security architecture, as well as configure IPsec peering between two devices. One of the major factors of network communication is the inherent security concerns that need to be considered. Internal network communication may be somewhat protected against external snooping and malicious attacks, but for internal communication, traffic may be transported freely over what is generally considered a trusted domain. This leaves a potential threat of snooping by internal users that may capture sensitive data and possibly even affect services. The more apparent communication concerns, however, are between remote locations, such as in the case of branch office communications. The Internet is understood to be a private domain that is shared by a range of users and open to a large number of threats, which leaves data vulnerable to attacks. Traditional approaches involve the use of private leased lines that were capable of providing an adequate level of security. However, the expense involved and the need for maintenance of the leased lines by the enterprise meant that it was not always an ideal choice. A solution was developed in the form of what we understand as IPsec, which effectively allows for secure network communication over such public network infrastructures as the Internet, thereby providing security whilst eliminating the expense associated with leased lines. We can understand IPsec to be a protocol suite developed for the purpose of securing IP transmissions between a source and destination. This is performed on the basis of ensuring confidentiality, integrity, and availability of the service. Confidentiality relates to the concealing of data and to some extent the packet itself, to ensure that the contents do not become known to unwarranted recipients of the data. In supporting integrity, IPsec protects packets from being changed from the point of transmission by the sender, thereby ensuring the packets themselves are not subjected to manipulation. We can understand availability to be factors that impact the service by degrading and even taking down service operations. IPsec also provides the means to maintain availability through preventing attacks that may be initiated by resending captured packets. The IPsec VPN architecture is made up of a suite of different protocols and frameworks that are responsible for securely negotiating the connection between two endpoints. However, the confidentiality, integrity, and availability of services are supported through two protocols, referred to as the authentication header and encapsulating security payload. The authentication header is designed to provide connectionless integrity that detects changes in the IP packet without concern for packet order in a stream of traffic. It is also capable of authenticating the origin of packets as they are received through hashing algorithms that act as fingerprints to ensure that the sending of duplicate packets in what is known as a replay attack is not performed. The encapsulating security payload is additionally able to support confidentiality through the implementation of encryption algorithms such as DES, triple DES, and AES. As computing power increases, however, the ability to maintain security becomes ever more difficult. In the case of DES, it uses a 56-bit key that in today's world does not provide a secure enough level against brute force attacks that rely on strong computational power to test all combinations of a key before the correct key is eventually discovered. As such, we often find encryption used in the form of triple DES or the advanced encryption standard that provides 168-bit and 256-bit encryption keys respectively. However, key size also requires more processing time, and so a balance between encryption levels and encryption-decryption processing time is generally needed. The Security Association, or SA, is another component of the IPsec security architecture that represents a unidirectional construct that is used to effectively bundle together a number of protocols and algorithms that are necessary to support the establishment of communication between the source and destination. These include defining whether AH or ESP will be used and the algorithms that will be used to support the applied protocol, as we have just seen. Since the security association is applied in only one direction, it is necessary that an SA also be created in the opposite direction and contain protocols and algorithms that match the SA to which it is paired. We can see from the example shown some of the typical parameters that are also carried within the SA that are unique to the SA, but are required to support the establishment of the connection between the two endpoints. Communication between the endpoints may be established through one of two modes, referred to as the transport mode and tunnel mode. In the case of the transport mode, we show here which parts of the datagram that are subjected to IPsec are authenticated and which parts are encrypted, where the authentication header and where the encapsulating security payload are applied. We generally find that the authentication header is capable of providing authentication for the entire datagram, with the exception to select portions of the IP header, whilst the SP is capable of supporting encryption of data and the respective upper layer protocols. We also show here where both the authentication header and the encapsulating security payload are supported together. However, to achieve this, a separate pair of SA need to be created for each protocol. When we contrast with the transport mode, we find that we are able to support in the tunnel mode what is known as traffic flow confidentiality, which is achieved through including a second IP header that acts as the outer IP header for securely transporting secure traffic. Through this means, the internal IP can be encrypted where ESP is applied, and as such disguise the true destination of traffic when being carried between the IPsec VPN tunnel source and destination points. When a packet reaches the tunnel destination, it can be decapsulated and make the final leg of its journey based on the inner IP header that contains the IP address of the true source and destination of the packet. Establishment of an IPsec-based virtual private network requires that a number of steps be performed. We demonstrate this in 5 stages here that begins with ensuring that network layer reachability between the source and destination of the virtual private network is possible. Since not all traffic will be required to be processed as virtual private network-based traffic, we must firstly perform filtering to determine which packets are to be determined as interesting traffic and processed, as well as which traffic is to be ignored and allowed to bypass the IPsec VPN encapsulation process. The filtering itself will rely on access control lists to distinguish the different traffic flows and identify which traffic will be classified as interesting traffic. For discovered interesting traffic, it is necessary to create a proposal that will determine the mode of transmission, whether transport or tunnel, and also the protocols that will be used, which consists of the authentication header and encapsulating security payload, along with the relevant algorithms supported for the selected protocol. In addition to this, a policy must be created that references the associated proposal and defines the parameters that will be used to establish the end-to-end communication of the IPsec VPN connection. Once the policy has been created, it will then need to be bound to an interface, which allows for the security association to be formed. With the steps we have just covered in mind, we can begin to look at the configuration steps that can be taken to establish an IPsec VPN connection between 2 points. We show a common topology here in which a connection is to be formed between devices RTA and RTB on the Gigabit Ethernet 0/0/1 interfaces for both devices. In this way, the entire IPsec VPN connection will be transparent to end users, such as those we show here in the form of host 10.1.1.1 and host 10.1.2.1. We start off by ensuring that the two end networks are reachable by establishing static routes. We show here the configuration from the perspective of RTA, in which a static route for traffic heading to the destination network of 10.1.2.0/24 should be forwarded to the next hop of 20.1.1.2. It is important to note that a similar static route will also be required on RTB to allow traffic to be returned to the 10.1.1.0/24 network via the next hop of 20.1.1.1. With IP reachability between the two endpoints, we can then begin to identify the interesting traffic which will be secured. An access control list rule is used to perform the filtering and determine that for traffic originating from the 10.1.1 network and destined for the 10.1.2 network, IPsec should be applied. Exactly what form of IPsec-based security is to be applied is determined in the proposal that we have named here as Tran1. This proposal by default will use tunnel mode, however can be configured to use transport mode if needed through the encapsulation mode command. We specify here that we wish to use the encapsulating security payload protocol, and that this protocol should use authentication algorithm SHA-1, while the default algorithm is MD5. For the encryption algorithm, however, the default is maintained. Through the display IPsec proposal command, we are able to view the results of the configured proposal and validate the parameters that have been configured. We find in this case that the tunnel mode is being supported and that the encapsulating security payload is being used as what is referred to as the transform set. With regards to this transform set, we have configured ESP to apply the SHA-1 algorithm and maintain the default encryption, which as we can see is DES. Since DES is generally less secure, it is recommended that for real-world implementations at least, triple DES or AES be used. The creation of the IPsec policy is required to define many of the parameters that establish the VPN connection, a policy we will name P1. In this instance, we are establishing the IPsec VPN connection manually, and therefore are able to view the various parameters that are involved in negotiation of a connection between 2 points. We will find that within the policy, we bind both the access list that defines the interesting traffic and also the proposal that we have just created to determine the transform set and relevant algorithms to be used to provide both encryption and authentication. The policy must also define the start and end points of the IPsec VPN connection, which is referred to here as a tunnel, with the local end being the gigabit Ethernet 0/0/1 interface of RTA and the remote end being associated with the gigabit Ethernet 0/0/1 interface of RTB. In order to support the security association, we also have a security parameter index that is used to reference the specific SA, and a key that is used to support authentication of the SA. The configuration of parameters here is in respect of RTA. For the SA created by RTB, the remote and local tunnel addresses, inbound and outbound SPI, and keys will be reversed. As the final part of the SA, the created policy that now references the proposal and interesting traffic and contains the parameters for establishing the IPsec VPN connection will now need to be assigned to a relevant outbound interface. The interface should be the interface that was specified as the local tunnel interface in the IPsec policy. We see here that the interface view for interface gigabit Ethernet 0/0/1 is entered and that the policy that we have named P1 is applied to the interface. If we wish to verify the results of the configured policy, we can use the display IPsec policy command. We show here based on RTA the configured policy that is named P1. We can verify that it is associated with the relevant interface and that the general parameters have been configured. We can verify that access control list 3001 has been associated with the policy along with other parameters, with just a selection of those parameters being shown here. The remaining policy parameters can be seen here with the relevant configuration to support the SA, as well as the parameters that are expected from the received SA of the peer. In order for the connection to be established, it is very important that the SA correlate accurately with the SA configured on the peer device. In summary for this section, then, we have just a couple of questions here. The first asks, what is meant by a security association or SA? We can understand a security association as being a collection of protocols and algorithms and relevant parameters that are used to enable the establishment of a connection between a source and destination. The SA itself operates in only one direction, and so must be paired with an SA of the peer in order to allow secure bidirectional communication to be established. What are the 3 possible actions that may be applied to IPsec filtered traffic? Well, traffic that is subjected to the IPsec filtering may either be discarded, forwarded normally, or be forwarded securely as a result of the IPsec